Good evening, everyone. I'm Nikhil from Texas A&M University. Thank you all for being here. My topic is experimental evaluation of prestressed concrete girders with low-shear reinforcements. So it's a lot of discussion about prestressed concrete girders now. But yeah, quickly going into a little introduction, we worked with Texas Department of Transportation. We work with Texas Department of Transportation. So it's a quick review of how the number of bridges and what's the usage of prestressed concrete in Texas. So right now there are almost 55,000 plus bridges in Texas that carry vehicular traffic. And based on a report in 2020 of condition assessment, almost like 48% are reaching towards the fair condition. That means they are not then they don't need to be replaced now, but they're in a condition where there are some significant issues or like damages or cracks. And as I mentioned earlier, like 50% of this is based off of 2020. So based off a report of now, it's close to 50%. And given that the increase in the infrastructure development, almost like 350 bridges on an average are being added to the Texas state's inventory. And of these, 61% are like the Texas I girders, just similar to the AASHTO type 1, type 2. These are developed based off, Texas I girders are developed based off the AASHTO girders. So with this prolonged usage and increased usage of these prestressed concrete girders, like we need to figure out why it's important to have accurate and better provisions and equations. So our our focus is majorly on the shear performance, particularly in the low shear reinforcement zone. If we have a girder design as a simply supported beam, there is a region almost in the middle of the beam, almost 30% of the bridge girder is governed by this minimum shear reinforcement provision. That's because the shear demand is pretty low. So it's if based on the calculations, we go to an equation called minimum shear, where the shear reinforcement is just provided to ensure deflection control and ductility of the beam, given that shear failure is very brittle in nature. As I mentioned, the shear failure is very brittle. It's because of that, the estimation of shear capacity at the first cracking, which is called cracking shear strength, and the final ultimate shear strength is the nominal shear strength according to the code provisions. These are very difficult to predict because in shear failure, because of these diagonal cracks, the plane section approximation changes. And this minimum shear reinforcement provision often rely on these two strengths. It's just that because this minimum shear reinforcement zone is to ensure ductility and safe transfer from post-cracking of concrete. So these minimum shear reinforcement guidelines typically rely on these two capacities. So if we take a quick look into these provisions, like we have AASHTO provisions that's being used by most states, most state DOTs, and we also have ACI provisions, which are the design equations for this minimum shear reinforcement. And if we look into text.bridge design provisions, they typically adopt AASHTO design equations and also have a updated maximum spacing provision based on their constructability and sizes of the girders which are in practice. And if we look into the factors that affect shear performance based on like various tests in literature that happened over the past few years, there are like various factors that govern the shear performance, like starting from the spacing of the shear reinforcement, which is the force taken by the stirrups, and then concrete tensile strength, yield strength of the stirrups shear reinforcement which you are putting in, and the shear span to depth ratio. And if we take a look into the effects of prestressing, we have presence of hard tendons and also the level of prestressing, and finally the depth of the beam, which typically governs the size effect. So we have these so many factors that govern the shear performance. So it's very difficult to develop shear prediction or shear capacity equations because it relies on a lot of factors. So that's where our experimental program comes in. Our idea is that we figure out all these factors and do a comprehensive study on full-scale tests and try to see how much it impacts how much each parameter impacts the shear performance from the cracking towards the ultimate strength. So we started with an design of the experiment, like how we are going to put these in the specimens, how we are going to test it, and then the design of the test specimens itself, because even though we have a specimen, it's again a prestressed concrete girder, it should be safe for construction as well. And after that, we look into the instrumentation and the large-scale testing, and finally some results. This is how our experimental specimens are designed. As I've shown earlier, let's say we have a simply supported bridge girder, and there is a region, it's governed by the minimum shear reinforcement provision. So we try to put it in a 4-point bending configuration, because in this type of configuration, we have 2 zones of constant shear. And if we vary the shear reinforcement based off of whatever we are calculating, in these 2 regions, we have 2 tests per each girder. So let's say we are designing this girder based on a particular number of pre-stressing strands and particular number of shear reinforcement and a varying concrete strength. For each of them, we have 2 tests. So like if we test one girder in this 4-point bending test, we have 2 zones of effective testing. So we can vary the shear spacing based on whatever equation we are comparing in that case. So as I mentioned earlier, we have like so many factors. So trying to get a comprehensive test matrix out of looking into all of them is quite difficult. So we try to touch base with each of them so that we have a comparison for each of these parameters. So starting with the yield strength of stirrups, like the shear reinforcement, and then the spacing from different provisions. So we compared the typical maximum spacing provided by TechStart and also the minimum shear reinforcement spacing obtained from ACI and AASHTO. We also have looked into the effect of harp tendons, where we compare shear performance of a girder with harp tendons and without harp tendons. And we also looked into the effect of shear span to depth ratio, how it affects the safe transfer of girder performance from cracking towards the ultimate. And we also look into the effect of concrete strength and number of pre-stressing, like this is the pre-stressing ratio, but if you look over here, we varied the number of pre-stressing strands for the safe design. And in addition, we also looked into the size of the girder. All the other specimens are TX54, and this is a TX70. TX54 meaning is 54 inches deep, and 70 is 70 inches deep. So the reason why we selected TX54 is that we looked into different design specimens, prototype designs of all these TechStart practice girders for these eye girders. And after the size of, after the depth of the beam that's greater than 54, that's when the girders will have most region controlled by this minimum shear reinforcement. And these are the girders which are in high practice. And we also looked into development of database, and just to compare how original the contribution of these tests to these to the existing literature, which already looked into some small scale and reduced scale specimens. So here on the left, you have a comparison between the cross-section height and yield strength of shear reinforcement, which was studied. And given that our girders are pretty deep, so and we are also testing in full scale, we have some unique combinations where it's, when combined with the database, we can use it for database analysis in the future. And also, if we compare with effective pre-stressing ratio, it's like the number of, which is governed by the number of pre-stressing strands and the concrete strength. And even in that case, with the cross-section height, there are very less number of tests that are being done, and the stars are our test specimens. So it's a significant contribution to this database. And after these specimens are designed, like what we have shown in the test matrix, these are constructed based on our requirement, given that the designs are different, because the minimum shear reinforcement is typically provided in the center of the girders, but for our specimens, we need them in the region where we are testing. So we need to make sure that the rebars are placed at the selected spacing, not any different. And this is a 3D model of the test specimen testing setup. As I mentioned, this is a 4-point bending so that we have 2 zones of constant shear. And this is a picture of the specimen from our lab. So the beam you see here is a TX54, like 54 inches deep and 50 feet long. and each testing zone is 16 feet, and it depends on the selected A by D ratio, shear span to depth ratio for that specimen. And along with the testing, we looked into instrumenting of these girders so that we have comprehensive data that can be analyzed to identify significant variations in the performance, starting with strain gauges, where we installed steel strain gauges on the stirrups before casting of these girders. And we also have concrete surface strain gauges on the top of the girder and the bottom of the girder, and also monitoring the strains along the probable crack formation angles. And in addition, we also have string potentiometers at the bottom of the girder to track the vertical displacement of the girder as the test progresses. We also have LVDTs and load cells. The LVDTs are installed on the web of the girder to calculate the principal strain of the web surface of the girder, and the load cells to get the reaction force. And these are a few pictures from the lab setup. So like on the left, you see the full girder and instrumentation that's set up. Yeah, so given the constraints in the lab, I wasn't able to take a full scale picture, but I was trying to put that so that you can see every different aspect. And with that, we test all the girders. I'll quickly show two significant parameters which we were talking about, which are the major steps, the cracking strength and the ultimate strength. So this is a video from a test where we see the cracking strength at the first crack. Given that the crack is very, very thin, it's like 0.15 inches, I think, yeah, 0.15 inches. So it's pretty difficult to see. But when we see the ultimate failure, we try to fail it in shear, which we do not want in a bridge girder. But yeah, so we tested all these girders in shear based on the selected testing configuration for all the girders. So first, we start with a comparison of this prediction or estimation of cracking strength, where the blue line you see is comparison between ACI concrete contribution, which is taken as cracking strength here, and the experimental cracking strength, which is the shear strength at the first crack. And the other one, the orange one, you see is AASHTO. From a quick glance, we see that majority of the cases, ACI is kind of overestimating the cracking strength. This might be the reason because they are also including the harping properties. But when we look at the AASHTO, it's always under. So, but when we look into the ultimate cracking strength, the same comparison for ACI and AASHTO, all of them are mostly less than 1. That means the experimental strength is always greater. Since we discussed all these major parameters that affect shear performance, we quickly look at how these can be compared given that we have all the data. So first major factor that we looked into is called Reserved Shear Strength Index. It's a ratio between shear strength at failure versus cracking. So this ensures that post the cracking strength of a girder, after which the concrete is cracked, the stirrups come into play. So this ratio ensures that there is a safe performance of the girder even after the first crack. This is a good measure of a ductility of the girder, given that shear failure is pretty brittle in nature. And we also look into the shear force versus displacement plots and comparison of crack measurements like angles, density, and width. And we also look into the yielding of strain gauges from the stirrups, girder displacement profile, and the concrete strain profile along the section as the test progresses. But given that there are so many tests and so many comparisons, we try to focus today on the RSS aspect, because that's what governs the development of these minimum shear reinforcement provisions. So I'll show an example of how we look into all these different comparisons. So first, we have comparison of effect of shear reinforcement spacing. So we have 3 specimens with 3 different spacings: 18 inches, that's the TxDOT standard practice, and 26 inches, that's the minimum shear reinforcement from ACI, and the 38 inches is from AASHTO. this is not including the maximum spacing provision. We are only looking into the comparison of this minimum shear reinforcement equations performance. So if, as we have seen earlier, that ACI's cracking strength prediction is a little higher, and when we look into the comparison of ultimate strength, ACI's nominal strength equation is pretty close to what is seen in the experiments, so that's a good thing. And when we compare AASHTO for the ultimate strength, the value is pretty significantly low. And when we calculate the RSS, reserved shear strength for all these different spacings, so we can see for the blue is the experimental, we can see that as the spacing increases, the RSS decreases because there are less number of stirrups intercepting each crack, which is also seen by the codes, but the performance decrease is not as significant as what is being shown by the code. So like if we are considering about increasing the spacing of shear reinforcement in those zones, it can be improved. And we also look into the crack measurements of widths and angles. If we see the comparison of crack widths, the crack widths are significantly higher for the last case. These measurements are taken like at the first cracking, like these, and we did not take any crack width measurements close to the failure, given that the girders are like blasting off. We had to put a blast shield and we were staying behind. And that was a comparison of shear reinforcement spacing. And if we look into the yield strength of stirrups, this is a comparison between 60 KSI stirrups and 80 KSI stirrups. We tried to have same VS contribution of stirrups to the shear capacity. So when we compared for these two different cases, we kind of observed that there is a little decrease in RSS compared to almost similar to what is seen by the codes, suggesting that we can use these higher strength stirrups. And next we look into the concrete tensile strength. We can see a significant decrease in the RSS as the concrete strength increases. Like we anticipated a F-C of 5, 7, 8.5, but the 28-day strength and the test day strength are a little high. But still we were able to get a good comparison where we observed that because of high increase in the strength of concrete, the RSS is reducing because there will be higher forces for redistribution. So given the increased usage of UHPC and higher strength concretes, so this should be looked at given that there is a drastic decrease in RSS. And if we look into the effect of prestressing strands, harping, we compared the girders with and without harping for different cases of spacing. We've seen that the harping typically increased the RSS as we assume because of the harp tendons, there's a vertical component of prestressing force that contributes to the shear performance. And we have effect of prestressing ratio with increase in the prestressing strands. There is a decrease in the RSS. Again, that is also because of the redistribution of stresses post-cracking into the stirrups. And next one, we looked into the effect of shear span to depth ratio. We observed that for larger, this is for the 4, the larger one, as the shear span to depth ratio increases, even though if we see a reduction in ultimate shear capacity, there is an increase in RSS. So again, it implies that it is showing good performance because more number of stirrups pass each of these cracks. And we also looked into the size effect of the girders. The first one you see is a TX70 and next one you see is a TX54. Even though because of the girder depth, you see the ultimate strength to be really high, the RSS is less than what you see in TX54. This is because of the size effect where the smaller TX54 had confinement of concrete, result in a higher RSS performance post-cracking. And coming to my conclusions, we have seen that the impact of usage of higher strength materials like using higher strength concrete, we can see that the reduction of RSS is, can be clearly seen, which means that the amount of shear reinforcement being provided in that need to be looked at further. And we also seen the effects of shear span to depth ratio and the depth of the beam, which implies the significance of size effects. And given that the minimum shear reinforcement provisions are based off of tests way years earlier, like 20 years earlier, and some of them are based off tests on reinforced concrete, we should ensure that all these parameters need to be included for effective equations. And I would like to acknowledge the Texas Department of Transportation who funded us for the project, Texas A&M Transportation Institute and Center for Infrastructure Renewal for providing us the support with the lab. Thank you. Sorry, I went a little overboard. These are our contacts for LinkedIn for our group and